Okay, last time we have the back pressure valve, and we will go to continue the discussion. Now we have the intercooler, and uh, we already defined the intercooler and the function. We already state the function of this device. When we connect it into your refrigeration system, it's simply used to remove flash gas of the refrigerant during the operation. In removing flash gas, there is a power save in compression. Later on, we will determine the power save by computing the standard vapor compression system and try to compare it using intercooling device. When we connect intercooler device in the system, such as here in your figure, this intercooling system is what we call the water-cooled intercooling by using water-cooled heat exchanger. Note that the system is composed of two compressor, the low stage and the high stage compressor. Later on, we will going to compare the system into the standard vapor compression system using only one compressor and without water-cooled heat exchanger, and to see to it if there is really a power save or the reduction of power requirements in your compressor by using this water-cooled heat exchanger or intercooling with water cooled intercooler. Okay, so in your block diagram, we can easily determine the phase of the refrigerant upon entering and going out to each parts of the refrigeration system. So when we consider this compressor A, the refrigerant upon entering compressor air is considered saturated vapor. We consider this as 0.1. Okay, so this is considered as saturated vapor. You compress it isentropically, then you change saturated vapor into superheated vapor. High pressure, high temperature at low stage condition, since we are in the first compressor A, which is what we call low stage compressor. This superheated vapor coming from compressor A enters in a water cooled exchanger, so that the refrigerant, which is in superheated vapor condition, reject its heat and absorbed by the cooling water. This is a cooling water. Note that water going into the system, and upon going out, your water in is considered cold, and then when the heat is absorbed coming from this side, the refrigerant side, there is a heat going out to the refrigerant side and absorbed by the cold water going into your intercooler. Thereby, the condition of your water going out to your intercooler is considered warm. Okay, So there is a rejection of heat inside this device, your water cooled exchanger, and because of this intercooling, your cooling water, this one, cooling water, all of those heat coming from the refrigerator side is rejected to the atmosphere. So we have that QR. We can call that QR intercooler or QR in. QR in or QR heat rejected intercooler. Heat rejected coming from the intercooler. QR in. Upon rejecting the heat of your refrigerant side and absorbed by the water, cooling water, and reject all of this heat to the atmosphere. At point 3, since this is your point 2, at point 3, again the condition of your refrigerant at point 3 is once again converted into saturated vapor. Okay, your intercooler or water cooled heat exchanger is in constant pressure process also. Okay, so again your superheated vapor once again converted into saturated vapor, but of course the pressure involved in point 3 is the pressure correspond to your intercooler or water cooled heat exchanger. So since upon entering B or compressor B, it is once again saturated vapor, we have now changed the condition of your refrigerant from A, which is superheated, once again converted into saturated vapor. That is the function of your intercooler. Okay. Again, it is a device or accessory used in refrigeration to change superheated vapor, this one, to saturated vapor refrigerant. And because of this, there will be a reduction of power in your compressor, or there will be power save or reducing the work of compressor per pounds of vapor. Let us we will later on find the difference when we compute this system and try to compare this into a basic refrigeration system. Note that this is composed of two small capacity compressor. We will try to compare this again later on by using only one compressor with the same capacity of your system, condenser pressure, evaporator pressure, and the tonnage, and find out whether there is a power save using this system. Because from the definition, state that when we are using intercooler, there is a less power requirements compared to the system without intercooler. So let us consider later on the difference when we compute this later on. So again, you compress saturated vapor into compressor B. At point 4, it is once again superheated vapor. High pressure, high temperature at high stage. This side is at low state, the other one here is high stage. And then the superheated vapor once again converted into saturated liquid. Since there is again a rejected heat coming from the refrigerant inside the system, and you reject this into the atmosphere using another medium. You can use air or water. Once again, another cooling water coming cooling tower or a high velocity air that will absorb or reject all the heat coming from the refrigerant side, then later on convert that into saturated liquid. Then this saturated liquid later on pass into your expansion device. Of course, this is at constant enthalpy. That's why you have a just straight vertical line going down until it will reach evaporator pressure. At that particular point, this is your 0.5 and then 0.6, your saturated liquid will once again converted into wet mixture at low pressure, low temperature, and then cycle continues. You absorb heat coming from the load and then change wet mixture into saturated vapor, and so on. Okay, so all in all we have 6 points here, and if we assign points, assign values, pressure to your condenser, let's say this is at 40 degrees, that is your condensing temperature, and we have evaporating temperature, let's say -10. At -10 degrees Celsius with, let's say, 50 tons capacity, then we can easily solve the masses, the power at point A and power for pressure at point B. We can also compute the heat rejected in your intercooler, as well as the volume flow rate at point A, at compressor A, and volume flow rate at compressor B, and then the heat absorbed in your evaporator, and then your heat rejected in your condenser. So using this data, we will try to draw first the diagram, the pH diagram, the system. Okay. So let us consider the diagram. So pH diagram. pH diagram system. Let us use ammonia. Okay, for NH3, of course there is a line, okay, correspond to 40. So this is your condenser pressure, correspond at 40. P condenser at 40 degrees. Okay, and we have, of course, evaporator pressure at -10 degrees Celsius. Okay, so this is -10 degrees, 40 degrees. Okay, to determine the pressure in between compressor A and compressor B, for intercooler, if the pressure of the intercooler is not given, then you can use this equation. Your P intercooler is equal to the square root of P condenser and P evaporator. Okay, so that is your pressure of intercooler. So in between this one, it is what we call P in, wherein P intercooler or intermediate pressure, we call this P intercooler pressure or intermediate pressure. Okay, intercooler or intermediate pressure is defined as the square root of the pressure of your condenser multiplied with the pressure of the evaporator. Okay, so that is in between condenser and evaporator. In this case, P intercooler is the pressure correspond at 40 degrees multiplied by the pressure of your evaporator at negative 10 degrees Celsius. That is your intercooler pressure. Okay, so that this point, at point 1, you consider this as your point 1 because upon entering your compressor A, it is saturated vapor. You compress it by isentropic process until it crosses this line, the corresponding intermediate pressure. Okay, so this will be your point 2, and the intercooler rejects the heat absorbed by the water. Okay, so that at point 3 it is once again converted into saturated vapor. Okay, now again, in your definition, intercooler change superheated vapor into saturated vapor before entering the high stage compressor. So upon entering high stage compressor, the condition of refrigerant is once again saturated vapor at point 3, and then you compress it once again to point 4, okay, by isentropic constant, or constant entropy or isentropic procedure in your compressor. Okay, and then there is a rejection of heat in your condenser, so that at point 5 it is once again saturated liquid. The saturated liquid enters the expansion device, this one here, and at constant enthalpy it will go down, just straight going down until it crosses pressure correspond to your evaporator at negative 10. So this is straight line. This is now your 0.6. Okay, so that is your process. Okay, this one, H5 now is equal to H6 at HF 40 degrees Celsius. Okay, H1 of course is equal to Hg at negative 10. H3 is Hg at the corresponding P intercooler. Okay, P intercooler. Okay, we will transfer this to the other side. Equal. Okay, and then 2 and 4, enthalpy 2 and enthalpy 4 by chart. So you need to plot this into your chart using ammonia. So all in all, we have enthalpy 6, enthalpy 5, enthalpy 1, and enthalpy 3. Okay, we can now compute for the mass of refrigerant. Okay, to determine the mass of refrigerant, mret is equal to 3.5167 kilojoules second ton. We have 50 tons over RE in kilojoules per kilogram. Our RE is equal to, of course, our RE is equal to 1 minus 6 H1 minus H6, so that we have mass of refrigerant in kilogram per seconds. Okay, you can now compute for QA the heat added. This one, your QA is equal to mass rep multiplied by RE, that is in kilowatt. Okay, then after your QA, you can easily compute for your this one, power of compressor, PA. Okay, for your PA, it is equal to mass of refrigerant, that is the mass entering to your system, multiplied by work of compressor A. Work compressor A is just equal to H2 minus H1. Okay, so that you have your kilowatt there. Okay, we have also V flow at compressor A. Okay, and the mass of refrigerant entering there is also mass rate. Multiply that by specific volume at 0.1. V1 is equal to Vg at negative 10 degrees Celsius. Okay, let us first cut this.